Hey, welcome back everyone to History of Mathematics. We are going to continue working through Stuart Hollingdale's book, Makers of Mathematics, and we're going to hit chapter 13. Now, the title is a little strange. It's called Dalembert and His Contemporaries. So we've just discussed one of the big names in mathematics in the previous chapter, and that is, of course, Leonhard Euler. Now, the chapter after this one is perhaps the biggest name in mathematics, at least in the opinion of professional mathematicians, and that would be Carl Friedrich Gauss. So what Hollingdale did was he took a particular person that he felt embodied this period between the work of Euler and the work of Gauss. So we're using Dalembert as a representative mathematician from the period of 1750 to 1850. There are several other big names mentioned in this chapter, including the ones that your author refers to as the three L's. We have Joseph-Louis Lagrange, Pierre-Simon de Laplace, and Adrien-Marie Legendre, and all of them made big contributions to mathematics. So Dalembert is sort of right in the mix of all these things. He communicated with Euler about certain problems, made a lot of his own contributions as well, so the author focuses mostly on his work, and that's what we'll do in this video. So let's get to an example here of something called Dalembert's test. Let's switch over to the document camera. So Dalembert's test is probably more commonly known, at least in the United States, as the ratio test. Okay, so the ratio test is used to determine whether a series of constants is convergent or divergent. And the way the test works is that we look at this ratio. Now, this ratio is successive terms. Okay, so you're taking a term and dividing by the previous one. We're going to take the absolute value of that and let the limit of n go to infinity. So we're looking at the limit of the ratio of successive individual terms. And the ratio test tells us that if this quantity L is less than 1, then the series converges absolutely. If this quantity L is greater than 1, then the series is divergent. And the kind of middle case here, if L is equal to 1, we actually get no information. There are series where this limit is equal to 1 and the series converges. We'd have to establish that using a different test. And there are cases where this limit L is equal to 1 and the series diverges. So we can't really tell anything just from that. Just to refresh your memory from your calculus, converges absolutely means that the series of the absolute values converges. Okay, so if you had, say, an alternating series where it went plus, minus, plus, minus, plus, minus, plus, minus, like that, then it would still converge if you changed all the minuses to pluses. Okay, so let's get right into some examples here of using the ratio test. So I've got a couple that I want to look at right here. Okay, so let's look at this first series, n equals 1 to infinity of n over 3 to the n. All right, so in this case, a sub n is equal to n over 3 to the n. Okay, easy enough. So what I need to do is I need to look at the limit as n goes to infinity, absolute value, a n plus 1, and that would be this, over a n. Okay, so limit n to infinity. Okay, now both of these terms in this case are positive numbers, so I do not need to worry about the absolute value anymore. And of course I'm taking this fraction, dividing by this one, and we remember how to do that. To divide by a fraction, you multiply by the reciprocal. All right, so now we're left with this. Notice I've still got the limit here because I haven't taken the limit as n goes to infinity. Okay, now notice in my numerator I have a 3 to the n. Down here I have a 3 to the n plus 1. So this would leave me with limit n goes to infinity. Ugh, that's a crappy infinity sign. Let me redo that. N goes to infinity. And what I'd be left with is n plus 1 over 3n, and that limit is equal to 1/3. For example, you could find this limit using L'Hopital's rule. This right now is indeterminate, infinity over infinity, so you can differentiate the top and bottom and then take the limit there, and we get 1/3. Okay, so the limit that we were looking at in the ratio test turns out to be less than 1. And from that, we can conclude that our original series converges by the ratio test. Now, I will note that this test does not tell us what the series converges to. It tells us whether the series converges or not. It won't help us with what the series converges to. Okay, I would note also that this series cannot possibly converge to 1/3. Okay, some people get confused and think this number is telling you what the series converges to, but that's not true. In fact, the first term in this series is 1/3, and then you're adding stuff to it. So whatever this series converges to, it has to be greater than 1/3. Okay, the 1/3 is the limit of the sequence of successive terms, and the fact that that is less than 1 tells us that the series converges, but not what the series converges to. Okay, let's look at this next example here. Got n factorial over 10 power n. Okay, so we're looking at limit as n goes to infinity. Absolute value, a sub n plus 1 over a sub n, which is equal to limit n goes to infinity, n plus 1 factorial, 10 power n plus 1, n factorial over 10 power n. Limit n goes to infinity. Same trick as before, n plus 1 factorial, 10 to the n plus 1 times 10 to the n over n factorial. Okay, so notice what I've done. I've taken the reciprocal of my denominator and multiplied that. Okay. Now, we remember, of course, that n plus 1 factorial is n plus 1 times n factorial. Okay, a little scratch work there. Okay, so this is something that is pretty important when we're doing these ratio tests. We have to remember that every factorial contains all previous factorials in it. Okay, so for example, 6 factorial is equal to 6 times 5 factorial. It's another way to think of it. Okay, so we can do some cancellations here. limit n goes to infinity, n plus 1 over 10. Okay, notice the powers of 10 will leave me with a 10 in the denominator. And that limit is actually equal to infinity. Okay, this is not an indeterminate form anymore like this one was up here. Okay, in this problem, both the numerator and denominator were growing without bound. Here, the denominator is fixed and the numerator is growing. So the bigger n gets, the bigger this fraction gets. And that's why the limit here is infinity. So the conclusion from Dalembert's ratio test is that this series diverges. So in other words, the more terms I add, the bigger this sum is going to get. And the fact that this ratio is larger than 1 is what tells me that. So let's switch over to the front-facing camera again. Okay, so that ratio test is part of Dalembert's legacy to the mathematical world. Now, a big theme in this period, the period of time between Euler and Gauss, was the extension of calculus. Okay, so analysis, as it were, would reign supreme in this period of 1750 to 1850. And by analysis, what I mean is the extension of the ideas of calculus. So we're talking about differential equations, infinite series, all types of things like that. That was the main kind of focus of study in research mathematics at this time. And the author, Stuart Hollingdale, is using Dalembert as a representative for this time period. Okay, so we're going to have at least one more video on Dalembert. We're going to summarize some work with differential equations. We'll put a link right down there. We'll just kind of give the basics, and then we'll move on and continue our work